All right, hi everyone, welcome to VSPG. Today we're hearing from Jahandar Ramezani from MIT, talking about legacy uranium lead age data in Precambrian research, their utility, comparability, and limitations. So I'm going to go ahead and introduce Jahan for us, and we'll get to work. So Dr. Jahandar Ramezani is a geochronologist and chronostratigrapher applying high-precision uranium-lead geochronology to the stratigraphic record to calibrate Earth's geologic timescale. His research interests focus on the chronostratigraphy of marine and continental sedimentary basins, integrating their depositional history, biostratigraphy, and records of paleoenvironmental change. Jahan is diverse in his work, addressing methodology and Earth systems questions alike, and he's worked extensively on constraining the evolution of life and its environment in the Mesozoic. Jahan received his bachelor's degree from the National University of Iran in Tehran, and his master's degree from Memorial University of Newfoundland. He then went on to Washington University in St. Louis for his PhD with Robert Tucker. He then completed a postdoc at Washington University St. Louis and then a second postdoc at MIT prior to taking his current position as research scientist at MIT. Jahan is also a lecturer in the Earth and Climate Scientist Department at Tufts University. And we're excited to hear from you today, Jahan, so please go ahead and get us going.
Thank you, Alex, and happy spring equinox to everyone. I'm going to be talking about uranium-lead geochronology by the ID team's method today. I know Urs Schaltiger gave a talk last week, so he must have given a good introduction on the topic for everyone. It's just a method that we take individual uranium-bearing minerals, individual grains, and we spike them with the tracer of known isotopic composition and known concentration, and then we chemically separate uranium and lead by chemical techniques, and then the sample is basically loaded as a tiny drop on a filament, and it goes into a thermal ionization mass spectrometer and is measured. The isotopic ratios are measured. And this is the old-fashioned way of doing uranium-lead geochronology. It has been around for about 70 years. And since the beginning, there has been a major focus on Precambrian geology and Precambrian research, especially on the Canadian Shield. And as a result of that, there is now a large database of uranium-lead geochronologic data accumulated over a period of decades in Precambrian geology. And it raises some issues in terms of data quality, comparability, and utility of the legacy uranium-lead geochronology. And this is something that I would like to talk about it today. The main issue is trying to build like chronologies based on data that belong to different generations and different vintages of geochronology and different qualities. And a good example that I can give you is a paper published by Paul Hoffman a couple of years ago. And it's on the Paleoproterozoic development of the Great Slave Basin. And a table that we put together in this paper, it has got data coming from mid-80s. These are ages that are calculated, zircon ages calculated based on weighted mean 207, 206 age and Upper Concordia intercept ages, again from Baring et al. 1984. And there are two new dates in this paper. These are CA ID teams, or chemically abraded analysis on individual zircons, and the ages are derived from weighted mean 206 to 38 dates. And there are the more modern, we call CA ID teams type analysis. And between these two, you have got a whole variety of data from different times, from the 90s, from the 2000s. They are calculated from intercepts. They're calculated from 76 dates, and they are mix of multi-grain analysis, air abraded analysis, chemical abrasion analysis. So it basically raises the question how compatible these data sets are, and to what extent we can mix and match this data that have been accumulated over a 40-year period. There's even a whole rock uranium lead isochron age here from coming 1980. So the objective here is not to kind of denigrate valuable research done by my predecessors, some of which were truly pioneering work in their times, but rather to be kind of mindful of the underlying differences of these different data sets that belong to different vintages, and be careful when we're trying to compare them or compile them into chronologies. The first thing that I want to point out when you're comparing old data with new ones is that it's not just a simple matter of precision. Modern geochronology is not simply the precise version of the legacy geochronology. And in this case, you can see this is the work we have done on the left, on the Ediacaran or Avalonian granitoids of the southeast New England. I did with Meg Thompson's and co-workers. And you can see these are single grain chemically abraded analysis, 3 from dead-end granite from different locations, different outcrops. And these are all weighted mean 206, 238 ages of single chemically abraded zircons. The ages range pretty much close to 609 million years. And there's another date from a Milford granite, which is slightly younger at about 606 million years. And when you look at the legacy data from Zartman and Nader, 1984, you can see that this is a combination of Dedham Milford granite together, and it's an upper Concordia intercept date. And you can see that the age, reported age of 630 plus or minus 15 million years, regardless of being less precise, is actually doesn't overlap with new geochronology, even considering the systematic errors. And if you look at a little, dig a little deeper into this data, you will notice that each of those analyses on the Concordia plot are multi-grain zircon fractions, 10 to 20 milligrams of zircon in each analysis, meaning that they consist of hundreds of thousands of zircons. They were not pre-treated for lead loss. They used tracers made of natural isotopes as opposed to synthetic isotopes that we use today. So they had to be measured on different aliquots. Concentrations and isotopic compositions had to be measured separately on spiked and non-spiked aliquots. They were done on in-house mass spectrometers. There's not a lot of transparency of how these things were done and how the ages were calculated. But in any case, when you look at legacy data like this, you should not assume that they are accurate within the reported uncertainty. So just to give you a quick review, the uranium lead isotopic system consists of 2 independent chronometers. One is the uranium-238 to lead-206 decay scheme. The other one is uranium-235 to lead-207. And every time we make a uranium lead measurements, we come up with these two uranium lead isotopic dates from 206, 238 and 207, 238. 2 independent ages or dates are calculated. And then there is a third one, which is a lead 207, 206 date, independent of uranium, because we know the isotopic composition of present-day uranium, 137.818. We can substitute into this equation and get a lead date. And naturally, when these two dates agree with each other, we call them concordant, and it's a good sign. It's a sign of basically closed isotopic system, and it shows you that the age is reliable. Now, the first person that started this simultaneous treatment of the two isotopic or uranium lead chronometers and combined them into a plot that is now known as Concordia or Wetherill plot was George Wetherill. And it was very useful in terms of utilizing the open system behavior in uranium lead system and to extract additional information based on open system behavior for uranium lead analysis. And this is what the typical Concordia plot looks like. The analysis is shown by an ellipse. The 207, 235 date and its uncertainty is shown on the x-axis. The 206, 238 age and uncertainty on the y-axis. And you can see this is part of the Concordia curve on this plot. It is shown with a shaded error envelope, and that error envelope has to do with uncertainties in the decay constants of uranium-238 and uranium-235. And in case the isotopic system was not closed, it was open system behavior. And if we're lucky enough that it was a single stage isotopic disturbance or single stage isotopic resetting, and it was not episodic, it was not continuous, the analysis should line up on a Discordia line, the upper intercept of the Discordia with the Concordia curve give you the age of original zircon crystallization, and the lower intercept gives you the age of isotopic resetting, being lead loss or zircon overgrowth or some thermal event. And because there was a lot of discordance in Precambrian zircons, this was the method of choice for age calculation. Now, back in 1988, Ken Ludwig came up with an algorithm for mathematically combining the radiogenic uranium lead and lead ratios, and with taking into consideration of concordance in a quantitative way, and called it a Concordia age. It basically combines different uranium lead ages into one, and you can see that the error of this Concordia age is much smaller than the error of the individual analysis. So in this case, now we have basically 5 different ways to calculate a uranium lead date from a number of zircon or uranium bearing mineral analysis. One is the weighted mean 206, 238 date. Another one is the 207, 235 weighted mean date. Third one is weighted mean 207, 206 date. And then you have got the Concordia intercept dates. And then the fifth one is the Concordia age of Ludwig, 1988. And again, because Precambrian zircons had a lot of discordance, we're going to talk about it a little bit more detail later on. The method of choice for age calculation was used to be the upper Concordia intercept, general Concordia intercept, or the weighted mean lead 207, lead 206 date. Now, everything was good until 2005. Shaney et al. Published a paper based on high precision single grain analysis of well-behaved zircons. These were zircons that didn't have a lot of geologic complexity, and they produced a set of equivalent, very coherent data sets plotting on top of each other. It was not just zircon, there was xenotime, yttrium phosphate analysis too. And they demonstrated that all zircon analysis come out slightly discordant. They basically do not plot right on top of the Concordia curve, even though they're still within the error envelope of the Concordia, but they are not spot on top of it. And basically there's a systematic bias between 207, 206 dates, the lit dates, and the 206, 238 dates by up to 3.3% within internal errors. And then they had a long discussion about different possibilities, different sources of this bias. And by the way, this was not only from one lab. It was already known by that time from data from other labs, more specifically from ROM and GSC Ottawa, that this phenomenon actually existed. And then after ruling out all different possibilities, they reached the conclusion that this systematic discordance must have something to do with the inaccuracy of the uranium-235 decay constant. In other words, the Concordia plot is in the wrong place. It has to be shifted a little bit to the right so that it will fit the data. And for that reason, modern uranium geochronology has been more and more reliant on the 206, 238 chronometer and the use of other dates like Concordia intercept dates and the 207, 206 dates has been pretty much abandoned in high precision geochronology, and we are trying to work as much as possible with the 206, 238 chronometer. Now, why Precambrian zircon came out so much discordant? What was the reason for open system behavior? Well, first and foremost, it was a lead loss because the high energy alpha particles from the decay of uranium isotopes damage the structure of zircon crystals. This damage may range anywhere from lattice scale dislocations to metamectization of the zircon. It doesn't happen uniformly throughout the grain. It actually generates very fine scale uranium lead fractionation within the zircon grain, which can be exploited by weathering, hydrothermal alteration, and cause lead loss. And for that reason, because of that inhomogeneity in uranium lead distribution, the in situ analysis like laser ablation or SIMS analysis of zircon, they don't do any better than bulk zircon analysis by IDTIMS in actually overcoming the lead loss. And this metamectization is a function of uranium content and age. It accumulates over time. So naturally, Precambrian zircon, older zircons accumulate more radiation damage than the Phanerozoic ones. These are a few examples of zircon from Jack Hill's conglomerate. They're Hadean and younger in age, Archean in age. You can see in the top left, that's a more or less intact zircon. Top right, that's the beginning of radiation damage. The volume change basically causes cracking in the zircon and opens up pathways for lead to escape. And then in advanced stages of metamectization, in the lower right, you can see that the zircon basically is turned into an amorphous mass of zirconium oxide and silica. And basically there is the lead loss is at a level that cannot be overcome with any method or any technique of zircon pretreatment. Now, one of many contributions that Tom Crow made to uranium zircon geochronology was coming up with the technique of air aberration. And this is a method that you put zircons in an air abrasion device, and the zircon spins into that chamber, and the outer rims of the zircon, which are typically associated with higher uranium concentration and more radiation damage, are removed. And that was a big improvement in the accuracy of zircon uranium lead analysis at that time, and became a kind of a standard practice since the 1980s for all the zircon geochronology work. The other reason for open system behavior in zircon is the xenochrystic cores or zircon inheritance. These are the nuclei of pre-existing zircons that survive and are overgrown by younger zircon. Obviously, if you're doing whole grain analysis, you're going to be mixing zircon domains of different ages, and you're not going to get a meaningful, geologically meaningful age from this. These days, we can do zircon screening by backscatter electron or cathodoluminescence imaging, but in the old days, when they used milligrams and micrograms of zircon, there was no, obviously, opportunity to screen out xenochrystic cores, and that was another reason for open system behavior and discordance in zircon. So among other contributions that Tom Crow made to ID team's geochronology over the course of time period between 1973 to 1987 was coming up with acid digestion technique using Teflon bombs for zircon, uranium-bearing minerals, which greatly improved the blanks, the contamination of the samples, ion exchange chemical procedures for purification of uranium lead. He came up with magnetic techniques for zircon screening and separation, improved the quality of zircons for analysis, and also, as I mentioned, pretreatment of zircon by mechanical or air abrasion. And finally, 1987, the lead-207 synthetic isotope was introduced as a tracer or a spike isotope. And that also greatly improved the quality of uranium lead analysis. Another breakthrough that came in uranium lead geochronology in the early 2000s was the chemical abrasion, or CA-ID team's technique of Jim Mattinson. He combined thermal annealing and acid leaching, or partial dissolution of zircon, as a technique of pretreatment. And that was highly successful in overcoming lead loss, because acid could penetrate the internal zones of zircon and kind of mine out the radiation damage zones within the zircon crystals, which could not have been removed by conventional air abrasion. These were also the time, okay, so chemical abrasion, although it was very successful, highly efficient, was not, or is not, perfect. You can see data sets here from the same sample here from Oman. On the right is their air abraded analysis, and on the left side of the right plot, these are chemically abraded zircon analysis, and you can still see this blue analysis. They have sustained persistent lead loss, and they're excluded for age calculations. And most cases, this is because chemical abrasion has not been done basically right. Usually we do chemical abrasion anywhere between 190 to 200 degrees C. That's the partial dissolution by HF. And over the course of about 12 hours, but this is really not a one size fit all schedule, and you really have to optimize it based on the type of samples you're working on. And most of us in the geochronology labs are busy with our analysis. We don't have time to experiment with our zircons. As a result of that, chemical abrasion is not optimized in a lot of cases, and you can still get this persistent or residual lead loss in some of the CA-ID TIMS analysis. Okay, and then in the mid-2000s, again, came another big advancement in ID TIMS geochronology, and that was the Earth Time Initiative, spearheaded by Sam Baring at MIT. This was an initiative basically designed to overcome interlaboratory bias. It was designed to promote the best practices and protocols in ID TIMS geochronology, to a large extent standardize it, and have more transparency, accessibility to uranium-lead data. And as part of the Earth Time Initiative, new uranium-lead tracers were produced, were calibrated. They're being inventoried here at MIT, and they're being distributed to ID TIMS labs worldwide. Identification was done by on a lot of mineral standards for interlab comparisons. The synthetic age solutions, you can see here on the left, were produced so they can be measured in different labs, and they can be compared free of geologic complexity. A lot of intercalibration experiments were designed so the labs could compare their results, their data, their techniques. And also cyber infrastructure for data reduction, data archiving, and data accessibility were introduced. These are software packages and algorithms that now pretty much everybody use, so they can reduce their data in the same way, in a comparable fashion. And that was a major improvement in the technique and the type of data that comes from uranium-lead geochronology. This is one of the latest interlab comparison experiments that's been done. It's being under review right now. This was one zircon standard, large quantity of it. It was spiked and it was dissolved in one location, and it was distributed to 11 different ID TIMS labs. It was measured on 14 different instruments with different setups, different detector arrangements, and the results were all combined together on this plot. And you can see that all these 11 labs can produce results within 0.5 per mil of the age. And that's where we are today with ID TIMS geochronology. And the goal is in the next few years to be able to achieve 0.1 per mil reproducibility between all the participating labs using Earth Time protocols and practices. Okay, now at this point, I'm going to basically divide uranium-lead geochronology data or legacy data into different generations. So the first one, I would call it 1957 to 1973, the early days of UPB geochronology. 1973 being the introduction of acid digestion technique by Tom Crow. So a lot of this analysis were done by borax fusion technique, which introduced a lot of common lead, high blanks. It was a major obstacle in high precision, making high precision isotopic measurements. These were large multi-grain zircon analysis, milligram size samples. Hundreds or thousands of zircons were combined together in one analysis. There was no pretreatment done for lead loss of any sort. Traces were made of natural isotopes like lead-208 isotopes. The mass spectrometers were mostly in-house instruments built and operated in different fashions. The data reduction was not done in a standard way, and it was not transparent either. It was not being published, how the errors were treated, how the ages were calculated. And then next comes the Crow transformation era, I would call it, from 1973 to 1987, when the synthetic lead isotope spikes were introduced. And this time was a major improvement in uranium lead ID TIMS geochronology, as I mentioned, hydrothermal digestion of samples in Teflon, magnetic separation of zircons, improved sample quality, smaller multi-grain analysis going from milligrams to micrograms, and a fraction of the microgram in many cases. Air abrasion pretreatment improved the accuracy of uranium lead analysis. Synthetic lead uranium isotopes were introduced in 1987. Commercial mass spectrometers started to come online, so we have more coherent mass spectrometric measurements and done on the analysis, but you have to be careful because the Crow's improvements didn't catch on with the community right away. So you still see data from late 80s that are pretty much the same quality as the early days. And they have not basically implemented Tom Crow's techniques. And then the period from 1987 to around 2005, I would call it the era of steady progress. Some labs gradually moved to zircon, single zircon analysis, thanks to lower lab blanks and more precise and accurate measurements. I remember when I started geochron in the early 90s, going below 10 picogram of common lead lab blank was a major breakthrough for a lot of labs. Mineral standards were being measured a kind of informal way. They were being compared between different labs. The results were being compared. The mass spectrometer ion counting systems were developed at this time, in this time period. And we could measure smaller ion beams, smaller samples. And people also started looking into trace element and isotope fingerprinting of samples, of zircon samples, like hafnium isotopic compositions, and it started basically in the early 2000s. So a lot of improvement, steady improvement in this time period. And then comes the era of modern CA ID TIMS geochronology, or Earth time era. Chemical abrasion became standard practice. Community uranium lead tracers were produced and distributed to labs to overcome interlaboratory bias. There's a lot of formal interlab calibration experiments were being done, and they're still being done. Data reduction was more standardized using standard algorithms and software packages. Combined use of microbeam like laser ablation, SIMS analysis with ID TIMS analysis became popular during this time period, and there was a big improvement in sample characterization before ID TIMS analysis, and also Bayesian age modeling. Math is being used and is being developed to deal with complex age spectra of zircon analysis. So with that in mind, if you want to really evaluate data from different vintages, from different generations of uranium lead geochronology, if you're dealing with ages geochronologic data from the early days, These are not only low precision, the main issue with this data is questionable accuracy. It's just not possible to constrain the accuracy of this data in any reasonable fashion. This data have limited utility. And basically, if you want to say something is Archean or Proterozoic, this kind of data might be of use to you, but there's really not much more you can do about it. And generally speaking, these data require reanalysis. They need to be redone by modern CA-ID teams techniques, so it can basically overcome the problems of this generation, this vintage of data. And then data from the Crow transformation era, these are really a mixed bag. Again, not everybody used Tom Crow's techniques right away, so you still have a lot of data from different qualities, different vintages from this time period. It's difficult to assess the accuracy of this data. If you find statistically equivalent data sets that basically plot on top of each other, they can be useful, they can be reliable from this generation. A reanalysis necessary in many cases. Again, same issue with data from the early days. Now, data from the 1987 to 2000 or early 2000 time period, they have increased reliability. You still have to be mindful of that systematic bias between 207, 206, and 206, 238 dates. If you are going to compare them or compile them into a single chronology, you have to take that into account. There is some possibility for recalculation. You can import this data into modern software and recalculate them using more modern algorithms, using updated lab parameters. Some cases reanalysis might be needed if you really want to split hair with data from this era. You need to reanalyze at least some of them. And then in modern era geochronology, definitely there is improved reproducibility of this data. If you find statistically equivalent data, they should be highly reliable, and you shouldn't have any problem with using these ages. Again, you have to be mindful, chemical abrasion may not be optimized, so you might still get residual lead loss or persistent lead loss. You have to watch for it. With increased precision, always comes more data complexities. So things that we did not care about in the past, like prolonged zircon crystallization in a magma chamber, also known as anticrystalline zircons, now become more evident, become more pronounced, and you have to come up with strategies to extract an age, geologically meaningful age, from complex data sets as a result of increased precision of isotopic analysis. And by that, I'm gonna stop here. And if you have any questions, I will be happy to answer them.
All right, thanks, Jahan. All right, everyone. We're going to switch to questions and discussion. So you can raise your hand by finding that button at the bottom of your screen, click reactions, and your hand raises right there. You can also type it in the chat and I can ask for you. So John Valley, please go ahead.
Hi, Jahan. I really enjoyed your talk. It was a great summary, and it's nice to hear about the pioneering work that people have done over different years. One of the things that I think you didn't emphasize as much as could be is that there are some zircons that can't be done by the techniques you're describing. And there are zircons that are so complex when you look at their CL image that you need an in situ technique. even though it's less precise and maybe it's less accurate. But you showed a number of examples from the Jack Hills. Some of those examples, there might be something salvaged if one selected the CL domains that are not visibly altered. That has to be verified by analysis. But I think there really are some samples that can't be improved by doing all the modern TIMS work.
No doubt. TIMS still doesn't have the spatial resolution of in situ analysis. And the more we use in situ analysis in combination with IDTIMS, I think we get better and better results. But I totally agree with you. There are cases, zircons are so complex, they're so they have like multiple generations of zircons in one grain, especially in the Archean and older zircon, that you can really do much with it. And something I didn't mention, that chemical abrasion is really detrimental to metamict zircons. It basically destroys it in the course of partial dissolution. Partial dissolution becomes total dissolution. And that has been a kind of a drawback. But I personally believe if you start up with large quantities of zircon and you do the chemical abrasion, even intense chemical abrasion, and you're going to have a few survivors, and those few survivors still worth the analysis by IDTIMS. But yeah, I cannot agree more. All those techniques have to be used wherever appropriate.
Okay, thanks, John. Give a little time for anyone else who wants to ask a question. All right.
There's a question in the chat.
Oh, is there? I just
Okay,
completely missed it. Oh, okay.
Sorry.
I can read it for. Oh, go ahead.
How do you deal with common lead? I believe it's also called non-radiogenic lead. Yes. So a big improvement with IDTIMS has been lowering the common lead. And nowadays, pretty much everybody believes common lead doesn't come from zircon, especially if you do chemical abrasion. If there are any lead-bearing inclusions in the zircons, it's going to be all cleaned up, all removed. There are very, very rare exceptions to that. So nearly all common lead comes from lab blank. And for that reason, there's a lot of work been done in lowering lab blank. Right now, in most of those labs that I showed you in the interlab comparison experiment, the blank is below 0.5 picogram for sure. And we really strive for better than 0.3 picogram. To be able to do very small single zircon grains, if that answers your question.
All right, thanks. Next, Don Davis, please go ahead.
Yeah, I'd just like to point out as regards the common lead issue, our common lead has been reduced by an order of magnitude over a couple of decades without ever having actually changed the process very much. And I think the reason for that is just the general cleaning up of lead pollutants from the environment. A grain of dust today contains a lot less lead than it did, of course, back in Tilton's time when they used lead in gasoline. And we have Claire Patterson to thank for that, who pointed out the environmental danger of lead and promoted the efforts to try and clean it up.
Thank you, Don. Your idea is being tested in China right now. There are new IDTIMS labs that are being built, and they're basically struggling with common lead, figure out where it's coming from. So if you're correct, the Chinese labs are doomed, and it's going to take them a long time to overcome a lead lab. But we'll see.
Okay, thanks.
Sure, thank you.
All right. Just leave another couple seconds to see if anybody wants to go ahead and speak up. Okay, well, thanks a bunch, Jahan. This was super informative. I mean, even for me, it's good definitely for me, it's good to go over like a lot of what you went over early on was super useful for me as a refresher. So thanks a bunch. And good discussion at the end. So thanks a bunch, Jahan.
Thank you for having me.
All right, everyone, take care, and we'll see you next week.